Welcome to this video on dimensional analysis. In this video, we will explore how dimensions and units play a crucial role in simplifying equations, ensuring consistency in calculations. Dimensions and units form the foundation of measurement. They help us understand and quantify the physical world around us. A dimension represents a fundamental physical quantity, such as length, mass, time, or temperature. On the other hand, a unit is a standardized way to express that dimension. Let's consider some dimensions and their units. An example of a dimension is length. The unit most commonly associated with length used to measure length is the meter. The second example of a dimension is mass, which has the unit of kilogram. And a third example of dimension is time, which has the unit seconds. Each dimension has a letter used to describe it to avoid using the entire dimension's name in calculations involved in dimensional analysis. The letter for the length dimension is L, for mass we have M, and for time we have T. Now let's have a look at the principle of homogeneity. The principle of homogeneity states that all terms in an equation must have the same dimension. To illustrate this, let's have a look at an equation from basic kinematics, V equals U plus AT. V, an object's final velocity, is measured in meters per second. U, an object's initial velocity, is also measured in meters per second. A, an object's acceleration, is measured in meters per second squared. And time is measured in seconds. Now the dimension of the meter's unit is length, and the letter associated with that is L. So we'll write down L. And for seconds, the dimension is T. The same is true of the initial velocity, L over T. Now, dimension for acceleration is equal to L over T squared. And the dimension for seconds is T. Now, since acceleration is multiplied by time, this comes out to be L over T, which means that all the dimensions of each of the terms in our equation are the same. This is consistent with the principle of homogeneity. Now say, for example, we had made a mistake in our equation and we had said that V equals U plus AT squared. That means that this dimension here would have come out as T squared, which means that the final dimension of AT squared will have come out as L. This would mean that the dimensions are not consistent across each terms of our equation, meaning this equation is incorrect. So as you can see, we can use the principle of homogeneity to verify the correctness of equations. And to see the practical applications of this, let's have a look at a question. The period t of a simple pendulum is expected to depend on the length of the pendulum L and acceleration due to gravity g. Use dimensional analysis to determine a relationship between t, L, and g. So you know that t is expected to depend on L and g, we can say that t is equal to some function f of L and g. Let's have a look at the dimensions of each part of our equation. T will obviously have dimension t, L has dimension L, and acceleration due to gravity has dimension L over t squared. The principle of dimensional homogeneity tells us that the left side of this equation must have the same dimension as the right side of this equation, which means the right side of this equation must have dimension t. So we need to find out a function f that gives this a dimension t. This means that the two L's on the right hand side of the equation would have to cancel out. Now to do this, we can take g to the minus 1, making the dimension of this t squared over L. This means that the L's cancel. This means that the entire dimension of this section here becomes t squared. Now, we want the dimension to be t instead of t squared, so we can take the square root. So we have is t is equal to the square root of L over g. However, this right-hand side could be multiplied by a dimensionless constant. So t is equal to k times the square root of L over g. In other words, t is directly proportional to the square root of L over g. To verify this, let's have a look at the dimensions. T has dimensions t, L has dimension L, and g has dimension L over t squared. L over g, if we multiply both sides by t squared, we have L times t squared divided by L. The L's cancel, so we have t squared. Take the square root of this, so the dimension becomes t, and k times t, since k is dimensionless, will still have dimension t. And t is equal to t. This is consistent with the principle of dimensional homogeneity.